In this video, we talk about Doppler effect and power spectral density. So if you have a moving object transmitting a signal, then the receiver receives another random process, and then we want to see what's the relationship between these ones. So if a moving target, moving object is transmitting a signal S of t, so this signal is propagated on all directions and like 3D, and then your receiver at a given point receives a signal. Now suppose that either you or if your transmitter are moving. So if you're moving at time t on the direction of this v, so v bar is the vector, the velocity vector. At time t. Of course, v itself could be a function of time. Right now you are moving in this direction. 2 seconds later you may move in another direction. And suppose that then this v has an angle theta, and then you have some distance. So there is a relationship between transmitted signal and received signal. Of course, the received signal may receive signal from other locations, but I only consider here the component of the received signal which is originated from this source, from the transmitter. So the received signal, first of all, is attenuated or amplified depending on the gain of this channel and how far you are. So A is usually inverse proportional with distance, and distance is a function of the location of that, and to the power of alpha, and alpha may be impacted by the absorption of the waves, because these waves may be sounds or maybe electromagnetic, or there may be some obstacles here and so on. So I don't know A is random. A depends on the environment, is the gain of the environment. Here I assume A is almost constant, but A could be also changing with time. Then there is going to be a delay. This delay is equal to 2, is equal to distance, is a propagation delay divided by the velocity of wave. C is another velocity, or wave propagation velocity. So it's how fast wave is propagated. This speed is different with the speed of the object. The speed of the object is usually much smaller than the speed of wave propagation. And there are examples. For instance, some aeroplanes, they move faster than the sound that they are producing. In those cases, these equations still remain correct, and you can use them, but you can use the same equations and give you correct results. And what happens is that R here is the impact of some time. So it's kind of R is because you're moving during these propagations. So it's kind of like the waveform is either compressed or is stretched. So it's kind of the relative velocity. So it's going to be this relationship. So it's called Doppler effect. And 2 is, these 2 is the distance divided by the wave propagation velocity. And A is the attenuation gain. So how much is signal attenuated? Now, if I consider this signal, and S of t is a wide sensitization random process, I want to see what is the autocorrelation function of X of t. So we can use this one.